we need to talk about physics. As mundane and bookish as it might seem to some, physics is everywhere. It's in the clothes we wear, the food we cook, and old news to those perceptive few who already read the title of the video, the games we play. And that's what we're here to talk about today. How does physics affect your favourite games? Now, don't laugh. It's a lot more exciting than you might think. I promise. We start our journey back in 1972, and the first true video game, Pong, was taking its baby steps into the world. It was a simple creature with a simple premise. Play table tennis. Well, play physics-defying, world-breaking table tennis. If you've played Pong, and at this point, who hasn't, you've probably noticed that after a couple of hits, the little ball you're hitting back and forth seems to speed up. Normal stuff, right? The ball gets faster, so the game gets harder and more intense. Except it's not normal. When two objects collide, the speed at which they rebound depends entirely on two things, their momentum and their restitution. You've probably already heard of momentum. It's easiest thought of as the impact of a moving object, or how much it would hurt if it hit you. Momentum is very special in that in any given collision it must be conserved. The momentum before the collision is equal to the momentum after the collision. That's why things don't zoom away if they so much as touch each other. Restitution, in its most basic form, is a measurement of bounciness. It's defined by the material of two given objects and is a ratio of the difference between velocities after the collision to the difference before the collision. This number can take any value between 0 and 1. 0 means that they stick together or coalesce, and 1 means that they bounce perfectly off one another, keeping their original speeds. Seems simple enough, but it's this premise that absolutely tears Pong apart. Think about this. The paddles in Pong never actually push anything. They simply move into position and wait there for the ball to bounce off of them. And the ball speeds up. So let's say you have a ball that's moving at a given speed, say v. We're going to assume that the paddle is stationary before and after the ball hits it, making its velocity 0 at any given point. The ball hits, and it speeds up to a new speed, w. This would imply that the coefficient of restitution between the ball and paddle is w over v. As w is greater than v, however, this gives us a coefficient greater than 1, which, if you remember from before, can't exist. Well, we went and showed how Pong is kind of physically impossible. Sorry for any nostalgic people out there. Let's see if Pong's descendants did any better. Flash forward to 1999. It's almost time for the millennium. The human population has just surpassed 6 billion, and what better way to celebrate so many 90s kids by buying them a video game where all their favourite characters get together to knock 7 bells out of one another. That's right, I'm talking about Super Smash Bros. For the Nintendo 64. Now, I'm sure a few of you are aware that Smash has had a rocky history in terms of its accuracy. However, I see no reason why that should stop us doing calculations that are isolated around one Smash game, and that's just what we're going to do. Today, ladies and gentlemen, we're going to investigate the strength of a certain move in the game, and here to help me is the user of this move, the one, the only...
Show me a move!
Captain Falcon. So, how much power is the famous Falcon Punch packing? Well, for starters, it's one of the most powerful moves in the game, dealing a nice clean 20% when it connects. But to get a real sense of its power, we're going to need to use actual mathematical figures rather than an arbitrary percentage that doesn't mean anything. I mean, really, why is a percentage if it can go over 100? Before we begin, I'd like to give a huge thanks to the everyday gamers for unwittingly providing the amazing footage of 4 Captain Falcons going at it with only the Falcon Punch, without which these calculations would probably be impossible. Thanks guys, you're doing us all a service. So, looking at this clip in particular, we can see that when hit, Falcon flies in a wide, pretty much symmetrical arc. Already we can start to gather a few figures. First of all, I measured that the time that Falcon spends in the air is pretty much spot on 0.88 seconds, with half of that spent on his ascent and the other on his descent. We can also measure the angle he's projected at as being acceptably close to 45 degrees. Trust me, I measured this angle so many times, and 45 degrees is a good number. It's a number that will also help us massively. Finally, there's one more figure we need, and to find that we're going to need a tool. A very special, very useful tool. May I introduce the most helpful, most adorable scale of measurement ever to exist?
Hi!
Kirby! Kirby is one of few characters to be given an actual height in the Smash 64 instruction manual, being described as a an 8-inch high creature from a distant star. This tiny piece of information actually presents us with an incredibly useful tool. As Kirby is spherical, we can assume his height is equal to his width. And using Kirby as our scale, we can calculate the various lengths of parts of the stage that we want to investigate. For example, measured from the middle of the dirt path, we can see that Dreamland is roughly 16.75 Kirbys. Multiplying by his height gives us a length of around 11 feet, which sounds pretty reasonable. What we're going to be using Kirby for in this situation, however, is measuring how high Falcon is able to fly after being punched. The maximum point of his arc is roughly at the top of this tree trunk. A little bit lower, but there or thereabouts. This height is measured rather conveniently to be 4 Kirbys, 2 feet and 8 inches, or the more useful 81 centimeters. We'll use this number later once our first calculation is done. Projectile motion, thankfully, obeys a set of laws. No horizontal acceleration, the only vertical acceleration is due to gravity, all sorts of helpful stuff. One of the most helpful features of projectile motion is its relation between time, velocity, and angular projection. Using the equation on screen, we can use the figures we have access to in order to find u, the velocity and the direction of motion. The amount of time Falcon spends soaring majestically through the air is a clean 0.88 seconds. We already know the angle of projection, 45 degrees, and we can assume that acceleration due to gravity is just, well, acceleration due to gravity, 9.81 meters per second squared. Plugging those numbers into the equation gives us a value for u of 5.1 meters per second. Here's where things get finicky. We need to use a principle called the conservation of mechanical energy. This basically means that as long as no outside forces, such as friction, act on an object, we can assume that the sum of the energies it possesses at any given point is the same. The two main types of energy Falcon has, other than, are kinetic energy and gravitational potential energy. Kinetic energy is simply the energy of movement. You kick a ball, it gains kinetic energy and rolls across the ground. Gravitational potential energy, however, is a little harder to picture. Say you throw a ball upwards into the air. As it rises, it gains gravitational potential energy being at its maximum when the ball is at its maximum height. It's easier to think of gravitational potential energy as the potential something has to move back downwards. On the ground, potential is 0, at maximum height, potential is maximum. So, when Falcon is punched, he reaches a maximum height of 0.81 meters. In the instant he hits his maximum height, his vertical velocity is 0. This means that his gravitational potential energy is at its maximum. Using the equation energy equals mass times acceleration due to gravity times by height, we can calculate this maximum. For a mass, we're going to assume that Falcon is an average weight for a man around 6 feet tall because, let's face it, this boy is huge. So that puts his mass at around 68 kilograms or 150 pounds and gives him a gravitational potential energy of 548 joules. However, at his maximum height, Falcon still has a horizontal velocity. Since all the force is applied to Falcon instantaneously, we can assume his horizontal speed is constant. Therefore, at any given point along his path, his minimum kinetic energy is given by the equation 1/2 times mass times velocity squared. Plugging the numbers in with the horizontal component of his velocity, found with a bit of simple trigonometry, gives us a minimum kinetic energy of 122 joules. From Falcon's maximum height, then, to his point of impact with the ground, he must lose those 548 joules of kinetic energy since his minimum kinetic energy is constant. Since the fall is split evenly between ascent and descent, we can safely assume his time of descent is 0.44 seconds. Dividing this time gives us a rate of energy transfer, or power, of 1.25 kilowatts. Power, then, is force multiplied by velocity, and dividing by our calculated velocity gives us a final force of roughly 250 newtons. Now, before you get excited, that number is nothing. For a little bit of perspective, the average human can bite down with an average force of about 720 newtons. That's right, you, the viewer, can bite almost 3 times as hard as Falcon can punch. Humans are incredible. It's also unsurprising that this is nowhere near the average punching force of a martial artist. Through a series of experiments carried out in 2010, it was established that a karate black belt was able to throw a punch with an average force of 1,450 newtons, almost 6 times stronger than this poor guy's pathetic punch. This means that, sadly, Smash probably isn't a fantastic way to simulate actually getting punched in real life. Sorry to all of you who wanted to live that dream. However, it still stands that it is a fantastic way to watch all your favourite video game characters getting punched. Nothing more satisfying than watching a Pikachu take a punch to the face every now and then. So, if we're still not quite there by 1999, let's jump forward even more. 2007 and the Nintendo Wii has just been released. Love those motion controls. You know what else I love? Space. And so does Nintendo, apparently, because with the release of the Wii came Super Mario Galaxy, an instant classic and one of my personal favourite games of all time. This game is a bit different from your typical Mario platformer in that, well, Mario is in space. He's walking upside down, inside out, and all over funky little planets of all shapes and sizes. But should he be able to? Picture this. Well, you don't have to because I'm about to show you the clip, but hear me. Mario is scaling this tiny, tiny baby planet and he jumps off of its surface. Seems simple enough, but you know the drill by now, so let's get into it. We know that Mario is around 1.5 meters in height because of the life-size Nintendo-approved Mario statue that sold for nearly $3,000. Yeah, lots of people wanted this plumber in their life, including me. Using him as a scale then, we can work out three things. Mario's jump height, 2.6 meters, the radius of the planet, 2.8 meters, and the distance between Mario and the planet's center, 5.4 meters. Using that, we can work out the volume of our mini planet as being 95 cubic meters, and we can use that number to work out a mass. Mercury, the smallest planet in our solar system, has a composition of 85% molten iron. We could use that for our planet, but given how small it is, yeah, Mario doesn't want to be walking on molten iron. Can't say I blame him. So, because of our planet's size, we're going to model it as a uniform, or the same all the way around, ball of iron. Iron has a density of about 7,900 kilograms per cubic meter, and multiplying that by our volume gives us a mass of 732,000 kilograms, or 1.6 million pounds. Sounds huge until you consider that the mass of Earth is 6 trillion kilograms. So now we can use a gravitational field strength equation, shown on screen, to figure out the gravitational field of our mini planet. And plugging the numbers into our equation gives us 0.000017 newtons per kilogram. Compare that to the 9.81 newtons per kilogram we experience on Earth, and yeah, Mario is not staying on that thing. In fact, using calculations with his weight, one jump would send him hurtling away from the planet with an acceleration of 68 meters per second squared. Whoa! That is huge. So yeah, you jump once in Mario Galaxy, that's it. Off you go. Bye-bye. No cake for you. So, in terms of physics, games suck. But does that really matter? No one cares that Pong is impossible to recreate in real life. We're all just about having fun bonking some little balls around. And the increased speed is what makes the game fun. How dull would Pong be if the ball never sped up? Here's a clue. Very. And Smash Bros. Does it really matter that Captain Falcon in reality couldn't punch his way out of a paper bag? I mean, I'm sure having fun watching him beat the tar out of himself. Good for you, Captain Falcon. Smash wouldn't be the same without you. Keep punching those falcons. And I don't think I have to explain that Mario Galaxy would be nowhere near as enjoyable if Mario went hurtling off into space every time you pressed A. Although it would look interesting. Can somebody do that? Please, I would pay you some money to make that a mod. Look, at the end of the day, game developers aren't physicists, which is good. Games would be awful if they were made by physicists. You know why? Because we care more about accuracy than enjoyability, and that's not what games are about. Games are about going absolutely wild as your favorite characters, exploring lands, beating enemies, collecting items. So please, don't judge a game by the sum of its physics. Because as we've shown today, they don't really count for anything.